Okay, so continuing with all things eigenvalues. So, what more I want to say about sensitivity of eigenvalues and eigenvectors to ground-off error. So what I arrived at last time was the condition number of a simple eigenvalue, meaning that its multiplicity is equal to 1. Either multiplicity, algebraic or geometric, is basically it's the absolute value of secant theta, where theta is the angle between the left and right eigenvectors. For that eigenvalue. And so, and keep in mind how secant behaves, that secant 0 is equal to 1, so it's the eigenvectors are left and right are in the same direction, then it's perfectly conditioned that the condition number is only 1, but secant of pi over 2 is infinity. There's a vertical asymptote there. So when orthogonal and nearly orthogonal, that's when the eigenvalue is most sensitive. Okay. Now, in more practical terms, what this condition number means is that an order epsilon perturbation in A leads to an order epsilon times the condition number perturbation in the simple eigenvalue lambda. So if the eigenvalue is badly conditioned, tiny change in A could cause a very large change in the eigenvalue. Now that's the case where the eigenvalue is simple, multiplicity 1. It's a very different picture when we have repeated eigenvalues. I'll say a little bit about that. And I'll illustrate with a simple example. Suppose I have a matrix like this that is repeated eigenvalues, where you have some number A here that is non-zero. So this eigenvalue of 1 is defective. This is a kind of matrix that is not diagonalizable. So if I make a order epsilon change, so in this case, both eigenvalues are equal to 1. So now if I make a perturbation, where all I do is I just add an epsilon down here, and really the only element that would, off-cycle element that would change anything with the eigenvalues is in this 2-1 entry right here. What happens is the eigenvalues become 1 plus or minus square root of A epsilon. So notice that in the case of a simple eigenvalue, the power of epsilon was 1, and then it would be amplified by whatever the condition number was. But the point is still an order epsilon change. But when we have an eigenvalue of multiplicity 2 that's defective, the change is order square root of epsilon. So a more profound change, because epsilon is small, so raising it to a smaller power would make it larger. So in general, if you have an eigenvalue that corresponds to a Jordan block that is of size p by p, then an order epsilon change in the matrix leads to a change of order epsilon to the 1 over p. So in other words, the more defective the eigenvalue is, so the more generalized eigenvectors go with it, so the more of a gap between its algebraic multiplicity and its geometric multiplicity, the more sensitive the eigenvalue is. Okay. So these repeated eigenvalues, especially for non-diagonalizable case, can be quite troublesome. So this is only for unsymmetric. For symmetric eigenvalues, symmetric matrices, the eigenvalues are perfectly conditioned, the ones that are simple, and then the ones that are repeat, they still come with 1 by 1 Jordan blocks because they're always diagonalizable. So the eigenvalues are they don't really have sensitivity issues when it's the symmetric eigenvalue problem. So that's one thing that's nice about it, besides the fact that the eigenvalues are guaranteed to be real and the eigenvectors are orthogonal. Okay. Now, what's particularly interesting about sensitivity when it comes to studying the eigenvalue problem is that the discussion of sensitive eigenvalues versus sensitive eigenvectors are completely separate. They're not even correlated to one another. You could have eigenvalues that are sensitive to perturbations and corresponding eigenvectors that are insensitive, or vice versa, because the criteria or the conditions that cause an eigenvalue or eigenvector to be sensitive or not are very different. So to discuss sensitivity of eigenvectors, so we need some way of measuring sensitivity. So let's suppose we have this situation where we have an easily identifiable invariant subspace. So matrix A has this Schur decomposition, or at least, well, actually it doesn't need it to be a full Schur decomposition, so I'm going to erase that. But Schur would be an example of this, but that's okay, sufficient but not necessary. Where Q is broken down into as this block decomposition where we have R columns here and N minus R columns here. And T has this form. So T is block upper triangular. And here we have R rows and columns here, N minus R down here. Okay. Now, what this means is because of this block structure, the range of Q1 is an invariant subspace. So for instance, if it's dimension 1, it's an eigenvector. But for dimension greater than 1, the columns of Q1 are not necessarily eigenvectors, but we could extract eigenvectors from those columns. Okay. So the question becomes, how sensitive is this invariant subspace to changes in A? Now that can be difficult to measure, so I can define something to help us measure this. The separation between the matrices T11 and T22. Now this is a rather strange definition. I'm actually going to use a specific example to see how we can extract useful information from this. So I define as a minimum of this quotient of Frobenius norms So the matrices X, in this case, have to be dimension n minus r rows and r columns. And you'll see why from the multiplication we're going to use here. So T11x minus x T22 Frobenius norm over Frobenius norm of x. Okay. So because T11 and T22 are square matrices of different sizes, x is being multiplied on the right in this case, so the number of rows in x is, oh, I have this backwards, r by n minus r. So the number of rows in x is the number of columns of T11, which is r. The number of columns in x is the number of rows in T22, which is n minus r. So that's how you can see what the size of x is. Now, the idea is, and I won't go trouble showing this here, but the order epsilon change in A leads to an order epsilon over the separation change in Q1 in this invariant subspace. So in other words, if the separation between T11 and T22 turns out to be small, then small change in A can cause a large change in the invariant subspace. Now, what conditions bring about this separation between T11 and T22 being small? You can't really tell from this formula. So to give you an idea as to what can cause a small separation, I'm going to work with a specific example where we have Q1 being just a one-dimensional invariant subspace. In other words, an eigenvector. Okay, so we have, I'll set r equal to 1. So that means that Q1 is just a vector Q1, an eigenvector, and T11 is just going to be a 1 by 1 matrix. It's just going to be an eigenvalue lambda. And then, whoops. T22 is going to be an n minus 1 by n minus 1 matrix, and its eigenvalues will be the rest of the eigenvalues of A. So, in this case, we get a more concrete expression for a separation between lambda and T22. So, it's going to be the minimum over all basically row vectors. So capital X now is going to be a vector with 1 row and n minus 1 columns. So to make it easier, I'll just take the minimum over all unit vectors. And X will be, so T11 is just lambda. X is going to be a vector, and I want it to be a row vector, so that's why I'm taking the Hermitian transpose. Minus YH T22, and I take the Frobenius norm. And I would divide by the Frobenius norm of Y, but the Frobenius norm of a vector is also a 2 norm, which I'm already assuming to be 1. So basically, I'm taking care of a normalization already. So in fact, this is a vector. So I don't need to take Frobenius norm. Again, that's the same as a vector. That's the same as the 2 norm. Okay, so now I'll rewrite this as T22 Now, that would be the same as if I were to take the transpose of both sides of this whole thing. Okay. Now, when we consider the minimum 2 norm of multiplying a matrix by all possible unit vectors, what that gives you is the smallest singular value just as the 2 norm of a matrix is the largest singular value, and the 2 norm, the matrix 2 norm is also the maximum of the matrix A times any unit vector. So, the minimum gives you the smallest singular value. Now, singular values of a matrix are the same as singular values of its Hermitian transpose. So I get small singular value of T22. Okay. All right. So to not have this expression, but what does this mean? Well, here we use the interpretation of small singular value. So that is the distance from T22 minus lambda identity to the nearest singular matrix. Now, if lambda already is an eigenvalue of T22, well, that matrix is already singular. This distance would be 0. So really, it's equal to the minimum over all eigenvalues of T22 of the minimum distance between any of those eigenvalues of T22 and lambda. Okay. So that's how separated lambda is from T22. Is just the smallest distance between lambda and any of the eigenvalues of T22. So what does this actually tell us? It tells us that eigenvectors of clustered eigenvalues are sensitive to perturbation. Okay. So how sensitivity is governed? Sensitivity of eigenvalues is governed by how the left and right eigenvectors relate to each other. So parallel is insensitive, nearly orthogonal is very sensitive. Sensitivity of eigenvectors is determined by how the eigenvalues are distributed. So if they're clustered close together, the eigenvectors are more sensitive. If they're spread out, then they're not. So it's interesting how eigenvalues and eigenvectors affect each other's sensitivity. And that there's really no correlation between them. So for instance, you can have eigenvalues that are very well spread out. So the eigenvectors are insensitive, they're very well conditioned. But those eigenvalues could still be sensitive if your left and right eigenvectors happen to be nearly orthogonal. Similarly, you could have eigenvalues that so eigenvalues of a symmetric matrix, let's say, that are all perfectly conditioned because their left and right eigenvectors are the same. But if those eigenvalues of a symmetric matrix are closely clustered together, those eigenvectors are still very sensitive to perturbations. So in other words, all kinds of things can go wrong, or not.
Vector language on the second line, I guess it is,
Uh,
where it says YH times T22 minus lambda I.
yeah.
Okay, we can switch that because norm is like absolute value in that sense.
Yes, it is. Yeah, because and also what I'm doing, because really I'm taking the transpose of the entire vector, and
Pulling out the
yeah,
Y. Okay.
yeah. And since it's still a vector, it won't affect the two norm either.
Right.
Okay. All right. So that's the word on sensitivity of eigenvalues and eigenvectors. So now I can finally talk about how we can actually compute dang things. So the simplest method, it's extremely simple in fact, to compute an eigenvalue and eigenvector called the power method. Okay. So first of all, I'll give the algorithm in the middle to see what it does. So first, we need to choose an initial vector, call it x naught, that is, you can choose any vector as long as it's non-zero. Okay. Well, okay. I'll stick with be consistent with the notes. And just for uniformity's sake, we'll make it a unit vector. Okay. So, what you do is you take that vector and multiply it by A. And we get this vector, so QK we get ZK. And then what we do is get the next Q vector just by normalizing. That is Z. In the two norm sense. That's it. And we keep going until either these Q vectors converge, or it's apparent that they're not going to converge. So what does this algorithm actually do? If it converges, what does it converge to? So for that, I'm going to make some assumptions just for simplicity. So first, we're going to assume that A is diagonalizable. So we have a full set of eigenvectors to go with the n eigenvalues. And I'm also going to assume that we have the eigenvalues in this order, ordered by complex absolute value. Where the magnitude of the first eigenvalue is strictly greater than the rest, and between the rest of the eigenvalues, less than or equal to is fine. But that separation is important. Okay. Now, because the matrix is diagonalizable, the eigenvectors form a basis for the whole space. So what that allows me to do is express Q0, my initial vector, as a sum, a linear combination of all of the eigenvectors. Okay. So now that we have this representation of Q0, we want to take a look at what QK looks like after we performed K iterations. So QK is a vector obtained by multiplying by Q0 K times, but we had to normalize it after each multiplication to keep the size of the vector from getting out of hand. So I'm going to have some scaling constant, I'll call it beta K. We don't really care what it is in this case. So if I fill in this representation of Q0, then we go ahead and use linearity. We can move a to the k inside. Now, each of the x's are eigenvectors. So I can replace a to the k with lambda to the k. Now, another assumption that I also make here is going to assume, and for typical random vectors likely to be true anyway, that at least the first constant is linear combination C1 is non-zero. So now what I'll do is I'm going to break this sum up. So we have our first term, C1, lambda 1, oh, it's lambda I to the k here, lambda 1 to the k, x1, and then everything else. Okay. Then what I'm going to do is I'm going to factor out a lambda 1 to the k out of every term. Out of the whole thing. C1, x1. And then Ci lambda I over lambda 1 to the k. Okay. Now, this whole vector is a unit vector. So keeping that in mind, that this is the magnitude of it as a whole is manageable. So in other words, the magnitude is taken out of the picture because it's 1. So what we care about now is, as k increases off to infinity, what is the direction of this vector going to have? Because in other words, what in the sum is changing as k goes to infinity? Or really, what happens in here? Keep in mind the assumptions that have been made about the eigenvalues and their size.
Getting small.
What is?
Well, no lambda I over lambda 1 to the k, right?
Yeah, because lambda 1's the largest and strictly greater in magnitude than all of the others. So,
And k's are all positives.
Which are?
The K, the power K.
Oh yeah. We're letting K go to infinity. Yeah.
Right.
Yeah. So this is going to 0 as K goes to infinity. So the direction of his vector QK is the same as the direction of what? Of whatever vector. Which one? So what specific vector does QK have the same direction as?
ZK?
ZK.
Wait, what?
ZK.
Where do you see? Well,
From the algorithm.
oh no, don't forget that though. From over here. Yeah, that's true, but it doesn't help us.
XK.
Not XK, but
Beta K. No, is it a vector, beta?
it's a vector. Yeah.
It's X, it's just not XK, right?
We don't have an actual X. It's not a plain X.
Okay.
There's always a subscript. What's the subscript? No. All of these are going away. What's left?
X1.
X1. Yeah. This is the only thing that's still around. So all of these vectors, x1 to xn, have coefficients as linear combination. The coefficients keep changing. So the mix of vectors keeps changing. But the coefficients of all the other vectors are going to 0. So what ends up happening is K goes to infinity, QK converges to vector that's at least parallel. So it's a unit vector parallel to x1. So, and the thing is, now what you can do is, once you have, basically you're getting essentially x1, because I can prescribe that x1 is normalized to be a unit vector. So, a power method under these circumstances gives you the largest eigenvalue of A. And the, so if the power method converges, it yields x1 and lambda 1. So the largest eigenvalue and the corresponding eigenvector. Or at least I could say corresponding invariant subspace of one dimension. Okay, because any multiple of an eigenvector is still an eigenvector. Largest eigenvalue, just the one. Okay. All right. But these were some non-trivial assumptions that were made here. So it fails if the two largest eigenvalues have equal absolute value, but they're themselves not equal. For instance, suppose they have opposite sign, or they are complex numbers that have the same magnitude, but they're at different points in the complex plane. Things like that. Well, so for instance, if your matrix A is a real matrix that has complex eigenvalues that occur in complex conjugate pairs, if one of those pairs happens to be the largest among all the eigenvalues, then the power method will fail. Because components in the directions of all smaller eigenvalues will go to 0 still, but what you have could still fail to converge to anything. So you don't really pick up an eigenvector in that case. Okay. One thing, so I have some code on the site that implements the power method. And one thing I found is a little implementation detail is suppose the largest eigenvalue in magnitude is negative. What ends up happening is the eigenvector converges to a particular direction, but the actual components of a vector don't converge. They keep flip-flopping in sign because you're basically multiplying it by a negative value. So if you like normalize so that, like, for instance, the first component is consistently positive or something, then that can help. So it's little wrinkles that complicate matters a bit. So returning to the case where it can, well, also here's another thing to worry about. It is slow if the ratio of magnitudes is nearly 1. So we're assuming for convergence that the second eigenvalue is smaller in magnitude than that of lambda 1. How much smaller, though? So if it's a lot smaller, then this method will actually converge pretty rapidly because these quantities will go to 0 faster. But if that ratio is nearly 1, then it's going to take a lot of iterations. So that's another thing to be aware of. Okay. Now, the thing is, suppose you want all the eigenvalues, but power method just gives you 1. So what could you do? So if you're given x1 and lambda 1 that are found by the power method, you can use something I showed you last week, deflation. So you have a Householder matrix that has this structure where this part is all zeros, and you have this matrix B, and you can now use the power method on B to get lambda 2. And so you can keep deflating, and if power method will converge every step of the way, then you will get all the eigenvalues. Also assuming that the matrix is diagonalizable. So again, it's not the most reliable method, so I have a function on the site called I think called find eigs that actually uses this approach of power method and deflation. So if a matrix has eigenvalues such that power method will work, then you can use this. But it's not an approach that is recommended to just peel off one eigenvalue at a time using the power method. You get a nasty accumulation of round-off error. From this repeated deflation. Okay. So we need a more practical way to compute all the eigenvalues, but at least power method is still useful. We just have to find a nice way to generalize it to compute several eigenvalues and eigenvectors at once. So we're going to formulate a block version of the power method, and we'll do exactly that. Also, it's not a good idea, if you want all the eigenvalues, it's not a good idea to try to compute them using an eigenvector-centered approach, for a simple reason that matrices don't always have a full set of eigenvectors. Every matrix does have a Schur decomposition, though, and we're dealing with a decomposition involving orthogonal matrices, which are better behaved numerically. So we're going to go with that instead. So the generalization of a power method to a block case is called orthogonal iteration. And that also has a very simple statement. Okay, so you choose some matrix Q naught that is n by R, where R is the number of columns of your choosing. And you should choose it so that the columns are orthonormal. Now that's really easy to do because you can always just pick R of the columns of identity, any of those columns, and that will work. So what you do is, similar to the power method, you multiply your Q matrix by A. Now, in the power method, you've got your output, and you just normalize it. You might think, oh, let's normalize each of the columns to make them unit vectors. But we're going to go one step further. We're going to compute a QR factorization. And the result of that, the Q matrix involved, is what I'll call QK plus 1. I have it indexed a little differently in the notes, but you get the idea. So in other words, what you're doing is, you're not just normalizing the columns of ZK, you are making them orthogonal to one another. So you're orthonormalizing them. And you keep going until the Q matrices converge, or until it's apparent that they're not going to converge. Okay. Now, so the thing is, we have, if I multiply both sides of this by QK plus 1 transpose, and I have that relationship, but ZK is AQK. AQK. So what this tells us is if a Q matrices converge, so QK has a limit that I'll call Q star. So if we achieve convergence, then if I look at this matrix, QK star transpose A, whoops. I hate to change my notation to declutter things. I'm going to make the star a subscript rather than a superscript. So then I have Q star transpose AQ star converges to upper triangular form. And the reason why we can say that is, you look at this case, this matrix is always upper triangular, just from the details of the algorithm. But here, the indices are one apart. Here, the matrices are the same, but if the Q's are converging, these matrices are converging to the same matrix anyway, the Q star. So, that's why we end up with this, that this matrix is converging to this upper triangular form. And what else can be said is, using a similar analysis as what was done in the power method, the diagonal, and if it converges, if this matrix is R by R, so it has the R largest eigenvalues. We can also say that Q star spans an invariant subspace, or its columns do. So not eigenvectors. Like the first column, you could say is an eigenvector, but not the other columns. Okay. So So this block approach to orthogonal iteration can be used to compute several eigenvalues at once. So now the thing is, for convergence, we need this ratio of magnitudes of the r plus first eigenvalue over the rth eigenvalue to be strictly less than 1, or it will not converge. So in other words, we've kicked the can down the road as far as separation of eigenvalues. The power method, the second eigenvalue had to be strictly smaller than the first. So in this case, the first eigenvalue that's not going to be found must be smaller magnitude than the last eigenvalue that is going to be found. So that's what can be said about orthogonal iteration in general. Okay. So this would be more numerically stable, more robust than using the power method with deflation r times to compute the largest r eigenvalues. Okay. But suppose we want all the eigenvalues. What we can always do is take this orthogonal iteration to the extreme and let r equal to n. So we just keep multiplying by a, q or factorizing, multiplying by a, q or factorizing. But one thing to keep in mind, though, is the complexity of this is order n squared r, floating point operations. So let's suppose we let r equal to n, that's order n cubed, every iteration. We're talking pretty expensive here, but that's something that's going to be addressed a bit later on. But something really interesting happens in the particular case where r is equal to n. That will give us some insight on how to arrive at a better algorithm. Okay. So what happens in this case is if it converges, we get the actual Schur decomposition. Q transpose A, or Q Hermitian transpose AQ is equal to upper triangular matrix T, where Q is the limit as K goes to infinity of QK. All right. Now, okay, I might have some notation difficulties here because my indexing, I didn't remember how I wrote it in the notes, and I was too lazy to look. So the indexing is a little different here than what we have here. Okay. So here's what I'm going to do. Keep in mind T is upper triangular because that's what we get from the Schur decomposition, where the diagonal entries this is bad notation here, but the diagonal of T consists of all the eigenvalues, if we actually get it upper triangular form. Now, if a matrix has complex eigenvalues, we might not actually see that. And that's something I'll talk about when I get into the next section. But if the eigenvalues are real, then this is actually what you would see. Again, if it converges. Okay. Now, So I'm going to define TK to be QKHAQK. So this matrix is not upper triangular at first, but the idea is if QK's converge, then this will eventually converge to upper triangular form. So based on the algorithm over here, what I have is TK minus 1. Okay, actually, I'm going to leave it as TK. Now, AQK I have over there is ZK. But ZK, also from over there, is QK plus 1 RK. I'll group those together. Now, okay. So what I need is RK, which is QK transpose ZK. Okay, so we need to choose RK in the middle, which is all right. Look at TK plus 1. So that is QK plus 1, Hermitian transpose A, QK plus 1. And then I'm going to, now the thing is, the Q's now, unlike before, they always had n rows in R columns, but R is now n, so they're square matrices. So they're orthogonal, so the Hermitian transpose is the inverse. So what I'll do is throw in a QK Hermitian transpose right here, because that's its identity anyway. And then I have QK plus 1. And then I'm going to group these together. Now, AQK is ZK, so I'll fill that in. But ZK is QK plus 1 RK. But these cancel and become identity. So what's left is RK, QK Hermitian transpose, QK plus 1. Okay, so if you look at the final results for both TK, a few lines above, and TK plus 1, what is the only difference between them?
Between which two?
TK, the final step, and TK plus 1, the final step.
The RK left.
Transpose.
Well, not transpose, but yeah, what you were saying. Yeah, but multiplied in the opposite order. Yeah, so now the thing is, the other thing is, this is a product of two, well, unitary matrices, because I'd say unitary if they're complex, which it could be. The product of two unitary matrices is also unitary. But each RK is upper triangular because it comes from a QR factorization. So, and a QR factorization is unique. So what we have here, TK is equal to this. This is a QR factorization. Of TK. And then what happens is, another way of getting the next T, TK plus 1, is you take those QR factors and just multiply them in reverse order. Also, how do these T's relate to A? Well, you can choose Q naught to be any unitary matrix whatsoever. So, for instance, you can just choose it to be identity. So here's another way to describe orthogonal iteration. At least in the case that we've been talking about, R equals N. So you can just set T0 to be some initial unitary matrix Hermitian transpose A Q0. So for instance, I could choose Q0 to be identity, so T0 is just A. So now in your loop, all you have to do is compute the QR factorization, using whatever means, like discussed before getting to eigenvalues, whether it's a householder or Gibbons rotations. We'll talk more about that later. And then to get the next one, actually, I'll start K at 0. Okay. Just multiply them in reverse order. And that's it. That's the whole algorithm. And then if it converges, then this matrix TK, which initially is A, or something closely related to it, will hopefully converge to upper triangular form. And so actually, here's what is a good idea. Try this in MATLAB. So at the prompt, make a random square matrix of any size, and you can say, do a QR factorization, and then overwrite A by the product of those factors in reverse order. And I'm leaving off a semicolon in this case, so it'll print out the matrix. So what will happen is if you just make any random matrix, it has to be a square matrix, and try this repeatedly, you will see A converge to a somewhat upper triangular form. Now, if A has real eigenvalues, it will actually become upper triangular. But if not, you would see like 1 by 1 or 2 by 2 blocks. The 1 by 1s are for real eigenvalues, and the 2 by 2 blocks are for complex conjugate pairs. Now, what's also interesting is eigenvalues that are well separated from the rest, you'll see those exposed in the diagonal right away. But ones that are closely clustered, those will be your holdouts. It'll take longer for those other entries outside the upper triangle to go away. So you have to be patient. I wouldn't recommend trying this with a large matrix either. Just something you can see on your screen, like 6 by 6 or something. So it's a fun exercise to try to see this actually work. Okay. All right. Are there any questions about what happened with orthogonal iteration? So this is the simplest method that in most cases will give you all the eigenvalues of a square matrix. But now, see, how much time do I? Oh, not so much, but I can at least tell you the huge problems with that method. Besides the fact that it'll work most of the time. There are examples you could come up with where it would fail. But this method, as I've described, there are two huge flaws of it that need to be addressed. Okay. Now, okay. Okay. So, the QR algorithm so I'll call it version 0. Thanks. I don't even want to give it a non-zero version number. It's that bad. Where you just do repeat A equals QR, A equals RQ. So the first step is just the QR factorization, and then the other is ordinary matrix multiplication. Now, a QR algorithm is probably the most often used method for computing all BI values of a matrix. There are other algorithms, but chances are they're going to be used in special cases. But for general purpose, you're looking at it. But in fact, it was named one of the 10 most influential algorithms of scientific computing in the 20th century. But definitely not this version of it, a much more sophisticated version that I'm going to describe over the next couple lectures. The huge drawbacks to this approach. The first one that I'll address first is it's far too slow. It's order n cubed floating point operations per iteration. And each step is order n cubed because QR factorization is an n cubed operation, and so is matrix multiplication. So we need to address that first. And then even then, so we could actually cut it down to order n squared operations per iteration and for an unsymmetric matrix, and order n for symmetric by a pre-processing step. The other big problem is even after making sure your individual iterations are efficient. So I want to clarify. Each iteration is too slow. But on top of that, convergence is too slow. So not only are your iterations themselves too expensive, but you're taking too many iterations. So that's something else we can handle, where what we would do is, instead of taking QR factorization of A, we would shift A. So in other words, we're like subtracting off a multiple of identities, so you're only affecting the diagonal entries of a matrix. And we QR factorize that. And then we still multiply the factors in reverse order and add the shift back. So by choosing a good shift, you can dramatically speed up convergence. So at least we have ways of dealing with both those things to get to the QR algorithm as it's known today. Okay. So I can at least start talking about how the first problem can be addressed. Okay, so what we're going to do is faster iterations. Instead of working with A, we'll work with matrix H, which is a similarity transformation of A. And we want H to have a structure so that the QR factorization can be computed more efficiently than it can for a general matrix. So the question is, what should that structure be? Now, you might think, well, we're trying to reduce a matrix to upper triangular form. And we can use householder reflections, we already know how to do that, to make a upper triangular, so why not go ahead and do that? So step one, let's we can choose U so that U transpose A is upper triangular. So in fact, this is a QR factorization that would do that. Okay. Now, but here's the problem. That would mean that U transpose A, first column, has this form. There's some entry up here, and then everything else is 0. But here's the problem. To preserve the eigenvalues, we now have to multiply this matrix on the right by U. But the problem is, when we carry this out, this matrix, because U transpose had to affect all rows just to get this, multiplied by U on the right affects all the columns. So this 0 in here gets undone. So we've stepped on our toes, our own toes. Shot ourselves in the foot. So that's not a good idea. We didn't gain anything. Well, who knows what this column looks like after we multiply on the right by A. So what was the point? We have no assurance that we can get a matrix which is easier, cheaper to compute the QR factorization during the iteration. So let's try something different. Okay. Step 2, that we zero all entries after the second row. So we use like householder or Gibbons rotations. Might as well use householder for a general matrix. So that the first column will have some entries alpha and beta up top, and then zeros below that. Well, as a result of this householder transformation U never needed to touch the first row. It only needed to touch rows 2 on down. So it doesn't affect the first row. So now when we look at U transpose AU, and we multiply by U on the right, that does not affect the first column. So this is unchanged. So we did not step on our toes. We whatever entries we zeroed by the first multiplication are still 0 after multiplying the first time on the right. So the first column is now in good shape. So now we can repeat this process, move on to the second column. and 0 entries. That will still remain 0 after applying the same transformation on the right. So we can keep up this process, and the result is we get a matrix H that has Hessenberg, or the full name is upper Hessenberg, or simply Hessenberg form. Meaning that Hij is 0 if I is greater than, not J for upper triangular, but rather J plus 1. So the way it looks has this form. So it's upper triangular at first. But then we have one additional diagonal below the main diagonal that has non-zero entries. So the last 2 columns are full, and also the first 2 rows. Everything else is 0. So by being a little less greedy, I mean, we want to get A eventually upper triangular after the whole iteration is complete. But if we settle for a little less up front, making it Hessenberg, then we're in much better shape. And the reason why is in this matrix, these entries that I'm circling here, we only have n-1 entries to 0 in computing the QR factorization of this matrix. So what we use is n-1 Givens rotations. Each Givens rotation will work on 2 rows, so order n floating point operations each. So the whole QR factorization requires only order n squared floating point operations. So at least the first step at A equals QR over there, now is knocked down from order n cubed to order n squared. What I'll show starting next time is that when you apply the factors in reverse order, or multiply the factors in reverse order, you're just applying the same Givens rotations, no longer on the left to the rows, but on the right to the columns. So the amount of work is the same. So order n squared floating point operations per iteration. So we've already made this a lot faster, and then I will get into on Thursday how to speed up the convergence, so perform fewer and cheaper iterations. Okay, I know I'm past time. So we're getting there.